Let's look at the problems from the second test review for differential equations. So in problem number 1, you are given the closed curve in the plane, and this is the curve that you are given. We don't necessarily know what it looks like, but it's some sort of implicit relationship because we have the variables x's and y's, and we cannot easily isolate y. Our job in letter A is to show that the derivative, we have a differential equation here, we are to show that this is the derivative of this implicit relationship. Therefore, we're going to need implicit differentiation. So here we go. Term number 1, the derivative of x squared is just 2x because we're taking the derivative over here, you can see, with respect to x. Term number 2, the derivative of 2x is 2. Term number 3 is a y term. So remember, when you take the derivative, we're going to use the power rule. So I get plus 4y cubed, and then by the chain rule, the derivative of the inside, we leave a dy dx. Same thing with term number 4. The derivative of 4y is 4, and then by the chain rule, dy dx. And then on the right hand side, the derivative of 5 is 0. So I'm going to factor the dy dx term out of the 4y cubed and the 4, and I'm going to subtract all of the other terms to the other side, so I'll get minus 2x minus 2. Right, then I'm going to divide both sides by 4y cubed plus 4. I'm going to factor a negative 2 out of the numerator, and that will leave me with x plus 1. I'm going to factor 4 out of the denominator when I divide, and that will leave me y cubed plus 1. And I'm going to reduce that, and that'll give me the opposite of x plus 1 in the numerator over 2 times y cubed plus 1 in the denominator. And that's what they said the derivative was going to be, and that's what I got. So you have to show that implicit differentiation. In problem number 2, we are writing the equation of a line that's tangent to this curve, whatever it might look like. So when we write the equation of a line, so remember, you got to break down the problem, equation of a line. So I'm immediately going to write down, this is my target, this is what I want my finished product to look like. I already have the given point of negative 2, 1, so 2/3 of my work is already done. So I have y minus 1 equal to, I don't yet know the slope, I'm going to have to determine that, and then I have x plus 2. To determine the slope, my slope generator is here, so I'm going to substitute both the x and the y value into that, so the derivative at negative 2, 1 is equal to the opposite of negative 2 plus 1 over 2 times y is 1 cubed is 1 plus 1. So negative 2 plus 1 is negative 1, and the opposite of negative 1 is positive 1. 1 plus 1 is 2, times 2 is 4, so my slope is 1/4. So when I isolate y, I get y equal to 1/4 of x plus 2 plus 1. You can distribute the 1/4, but you don't have to for credit. In part D, which I think might be part C on in your packet, show that the equation from the given, so this is the equation from the given. My job is to show, that means I have to demonstrate. My work has to prove that the equation given from above is actually the solution to this differential equation. So basically what they just told me to do is to solve a differential equation, and they're giving me an initial condition or a point that I can use to find the value of c. So remember, when we solve a differential equation, we're going to separate, we're going to integrate on both sides, we're going to solve on both sides. So the first thing I'm going to do is separate my variables. Let me pull my screen down just a little bit so I have more room to work. I'm going to separate my variables by multiplying the 2 times y cubed plus 1 to the right hand side, and when I do that, I'm going to do the 2 integral, I'm going to get that coefficient out of the way, y cubed plus 1 dy, that's on the left-hand side. On the right-hand side, I still have the numerator of the opposite of x plus 1, and then the dx on the right-hand side. So my variables are separated. Probably makes a lot of sense to go ahead and when I integrate, I'm going to distribute the negative on the right-hand side. On the left-hand side, when I integrate, I get 2 times y to the 4th over 4 plus y. Remember, we're integrating on the left-hand side in terms of y. And on the right-hand side, I'm going to go ahead and distribute my negative and integrate. So I get negative x squared over 2 minus x. And remember to distribute the negative to the second term plus c. Don't forget the c or you won't get the right answer in this case. Cleaning this, now in this case, normally we get y by itself, but we can't because it's an implicit relationship. I can go ahead and distribute my 2 on the left-hand side. So distribute it to both terms, make sure. So I get y to the 4th over 2 plus 2y equal to negative x squared over 2 minus x plus c. Now I could get everything all on one side. I'm going to go ahead and substitute point negative 2, 1 so I can find the value of c, and then I'll go back and worry about getting everything on the correct side. So substituting a 1. So term number 1, 1 to the 4th power is 1 over 2. Substituting the 1 in place of y, so I'm substituting a 1, substituting a 1. 2 times 1 is 2. On the right-hand side, I'm substituting negative 2 in place of, negative 2 in place of x. So when I square the negative 2, I get positive 4. There's a negative in front of that, so that's going to make that negative 4 divided by 2 is negative 2. When I substitute a negative 2 in place of this x, the opposite of negative 2 is positive 2. So those are going to subtract out, and that's going to give me, or leave me with c on the left-hand side. On the right-hand side, if I change 2 into a fraction with a denominator of 2, that becomes 4 over 2, plus 1 gives me 5 over 2. So I have my value of c, so I'm going to come right back, remember, to where I left off, which is right here. And I'm going to substitute the c that I found. I'm also going to move, so I'm going to get everything over to the left-hand side. I'm going to move all these terms to the left. So on the left-hand side, I will have negative x, I just said I was going to move them, so I add that, and try it again. So I would add the negative x squared to the left-hand side and giving me x squared over 2. Moving the negative x to the other side gives me plus x. Now remember that c, we found it to be a positive 5 over 2. So when I move it to the other side, I get negative 5 over 2. Actually, the constant, I'm kind of looking, I can't see it, I pull my screen down. But since the original equation up at the top has the constant on the right-hand side, I'm going to leave the 5 halves over on the right-hand side. So I'll remember to leave that on the right-hand side when I substitute it in place of c. Alright, so let's come back where I left off. So I still have a plus y to the 4th over 2 plus 2y. I think I have all my terms. Yes, and that's equal to, remember, the 5 halves. Now, the equation above is, I don't currently have that, so what I'm going to do is I'm going to multiply everything by the least common denominator of 2. So, everything on both sides. So here, the left side gets multiplied by 2, and the right side gets multiplied by 2. So if I distribute that 2, that will give me x squared plus 2x plus y to the 4th plus 4y equal to 5. Alright, so let's compare that to the given equation. X squared plus 2x plus y to the 4th plus 4y equal to 5. So I have demonstrated, shown, proven that the solution to the differential equation that they gave me is what they said it would be. Problem number 2. The table below gives the values for the rate. So I want to pay attention to the fact that the values in the table are a rate, and they are measured in gallons per second, at which water flowed into, so the water flowing into the lake, with readings taken at a specific time. So here's my table of values. Oh, oldie but a goldie. Use a trapezoidal approximation to determine the average flow rate. Now, this is already flow rate. Our function is flow rate. So we're actually going to find the average value of flow rate. So remember, I inserted those words in there so I know exactly what I'm doing. This is an average value problem. So I am keeping my mind on 1 over b minus a from a to b of f of x dx. So for this specific problem, since we're doing that for the 60-second time period, our 1 over b minus a would be 1 over 60. We're going to divide by 67 seconds, and we're going to accumulate. Now, so far they haven't given me the name of a function, so we'll call it f of x to represent our flow rate. We're going to accumulate from 0 seconds to 60 seconds dx. So write up the calculus that you're doing, even though they asked us to do a trapezoidal approximation. All right, so now let's think about trapezoids. I'm going to come over here or up here and remind myself, okay, if I'm going to do trapezoids, the area of a trapezoid is 1/2 the base times the sum, 1/2 of the height times the sum of the bases. 1/2 of the height times the sum of the bases. Area of a trapezoid. Now notice they didn't tell me how many trapezoids, so whenever they don't tell me how many, then I put in what's reasonable to the data. So I'm going to put in trapezoid 1, 2, 3, 4, 5. I can get 5 trapezoids in that data, so that's how many trapezoids I'm going to do. All right, now, as you know, this 1/2 is going to be a part of all 5 trapezoids. So in this case, I'm going to take that 1/2 and I'm just going to have it out front all by itself. And then all I'm going to do for each trapezoid, so for trapezoid 1, I'll find the height and the sum of the bases. The height and the sum of the bases. So for trapezoid number 1, the height is actually this span right here, the interval. So that has a height of 10. Base number 1 is 0. I'm going to write that even though we don't really need it. And base number 2 is 10. Oh, wait a minute. That's the time. All right. So height number 1, base number 1 is 500 plus base number 2 is 400. So there's the half, the height, the base 1, the base 2. That's trapezoid number 1. I'm actually just going to put a number 1. Don't really do that on an assessment. And then trapezoid number 2 is going to be the span from 10 to 25. So the height is 15. Base 1 is 400. Base 2 is 350. That's trapezoid number 2. Trapezoid number 3, the height is going to be the span from 25 to 37. So that's going to be 12. Base 1 is 350. Base 2 is 280. That's my 3rd trapezoid. My 4th trapezoid has a span from 37 to 46. So that's going to have a height of 9. Base of 280 plus 200. Trapezoid number 4. And then the last trapezoid will have a span or a height 46 to 60. That'll give me 14. With a base 1 of 200 and a height of 180. Right, so that is my trapezoidal approximation. So something you should know, it's not a huge secret, but a lot of folks don't know it. On the AP test, you can actually leave your answer. Now, I think it did ask for, or we need to give the units, but you can leave your answer just like that as your final numerical proposed answer. You don't have to do the adding and the multiplying and the distributing and all that stuff. So my units in this case, let's see, what are the units? Gallons per second. So this is gallons per second. Now, how do I know that? Just to do another unit analysis, the 60 is seconds, so 1 over seconds. The rate is gallons per second. And in this case, dx would be our time, and the time is measured in seconds, and the seconds divide each other out, and we get gallons per second. Now, if you do the calculations on your calculator, you would actually get 312.083 gallons per second. But again, on the AP test, that would that would actually be wasting time, because your answer, as written above, would be showing your work and giving your final answer. In letter B, if the rate of water flow, which is what we've been talking about in this problem, is modeled by the function L of t, which is an exponential function, determine the average flow rate. So notice we're doing the same job, value of the average value of the flow rate, but this time instead of using a data set and instead of approximating, we have the actual function for the flow rate, and now we can actually find the exact flow rate. This is going to be a calculator problem because we don't know how to find the antiderivative of that function. So we're going to do the same thing. We're going to have the 1 over 60 second time period from 0 to 60 of L of t dt. And I'm going to pull my calculator up here in just a second, but I want to remind the folks who have an older model calculator of how to actually put this into your calculator. So when you integrate this on the older model calculator, just like the rest of us, you're going to put in the 1 divided by 60. And then when you press math number 9, it's going to type on your screen F int. So this is what it looks like on the older model. So whenever that happens, you're going to type the actual function of 500 times 0.983, and it will be to the x power. Then you need the comma. Then you need another x, because we're in terms of x. Then you need the lower bound of 0 and the upper bound of 60. So it's that way every time you integrate. You need the function you're integrating. You need the variable of x. It's always going to be x. You need the low bound, and you need the upper bound, and that's how you do that on the older model calculator. All right, on my calculator, I'm going to call up, first of all, I'm going to do the 160. 1 divided by 60. Close parenthesis, and math number 9, my low bound is 0, a high bound of 60. My function is not stored in y1. It might have been a good idea to do that. I haven't read the rest of the questions to see if I'm going to need that. So 500 point, oh, I have it written over here. 500, and that's times 0.983. Be careful with your typing. If you're like me, you can easily make a keystroke mistake, and that's going to change everything. Whoops, 983 raised to the x power, and dx, enter. So you get 312.922. Remember, you must have 3 decimal places. So 312.292. Right, so 312.292. Same units as before, gallons per second. So in letter A, we did an approximation, and in letter B, we calculated exact, and they actually weren't too far off. We had 312 in both cases, with negligible difference in the decimals. So for letter C, let's read that through. The first thing I see is how many. That is an accumulation. So you got to look for key phrases like that, how many, and now they want gallons. So we're losing the rate. So all the clues are in the decoding. How many is an accumulation? Gallons, well, the rate was gallons per second, so we're losing the rate. So everything here tells me that we're going to integrate for a 60-second period. So to lose the rate, I have to integrate from 0 to 60. I'm not dividing by 60 this time. I'm not looking for an average. I'm trying to accumulate. And instead of writing the function, I'm just going to call it L of t, because that's the name of the function, dt. And as long as, on the AP test, as long as they name the function, you are perfectly fine to write the name of the function. If they do not name the function and they just give you the expression, you may not name it yourself. You would have to actually write the function. All right, the calculator is going to do this work for me, and I had that integral in my calculator, but I had the 160. So what I'm going to do is I'm going to bring that same integral back. So I'm going to type second, enter. And what you'll notice is it brings back the very last thing that was on the screen. And I'm going to go back, and I'm going to delete the 1/60th. I guess I could take my answer that I had and multiply it by 60. But just to show you this feature of the calculator, delete. Be careful, because I always forget which order, if it deletes to the left or to the right. So just be careful. You start deleting the stuff you want to keep, and then you wasted your time. Okay, so there's my integral without the 1/60th. Like I said, you could have just taken your answer from the last problem and multiplied by 60. So we get 18,737. I'm never going to remember all those numbers, and when I hit my screen, it's going to 18,737,534. So here we go, 18,737.534, and we know that the units now are going to be gallons of water that flowed into, was it water? Yeah, flow rate. Water into the lake. So letter D, we are explaining the meaning of, which I just actually kind of talked about in the last problem. We know that from part C that when we write that integral, we are doing an accumulation of gallons of water that flowed into the lake. So I would say something like the integral 25 to 40 of L of t dt indicates the change in the number of gallons, should have typed this, of water that flowed, just stealing the words of the prompt, into the lake from 25 to 40 seconds. Now, it did not tell me to calculate that number. It just told me to interpret what it is. I mean, if you did, you could state that number in there. Instead of changing the number, you could have said, in this case, total number of gallons, or the number of gallons, or the amount of gallons. All of those would be okay in this particular case. In letter E, I can see that we are finding the derivative of a definite integral. I went ahead and grabbed L of t so I could see it. And when I find the derivative of a definite integral, I'm going to do three things. I'm going to take out the t, or the dummy variable. I'm going to put in the new function. For this problem, the new function is the upper bound of arctangent of e to the x. I see that the lower bound is constant, so I'm okay there. So take out the t. So here's what take out the t looks like. The derivative of the definite integral would be 500 times 0.983. And I'm going to take out the t. There is the take out the t. And step number 2 is to put in the new function. So I'm going to put in arc tan of e to the x. And step number 3 is to multiply by the derivative of the new function. So the derivative of the new function, arctangent of e to the x. So I'm going to need to find the derivative of arctangent, and I remember that the derivative of our arctangent is u prime over 1 plus u squared. In this case, u is equal to e to the x. So the derivative of e to the x is e to the x. So e to the x over 1 plus, and then I'm going to have u squared, so e to the x squared is e to the 2x. Remember, e to the x squared, when you have a power to a power, you multiply the powers. Now, if you had written, in just like I did here in parentheses, e to the x parentheses squared, and you left that, that would be okay too. That would be an acceptable answer. But that is the derivative of the definite integral. For problem number 3, we're going to solve some differential equations. So remember, to solve a differential equation, we're going to separate, integrate, and solve, depending on whether we can have an initial condition. I don't think any of these have an initial condition. So for letter A, I notice on the right-hand side, all of my variables are x, so all I need to do is to get the dx over on the right-hand side. So that'll give me 1 plus e to the 3x over e to the 3x plus 3x dx. All right, now I'm going to integrate on both sides. The right-hand side, I have to think of a strategy. I'm thinking u substitution, so I'm going to let the denominator equal to e to the 3x plus 3x. The derivative of that, the derivative of e to a power is e to the power times the derivative of the power, and the derivative of 3x is 3. I can factor out the 3 and divide it to the other side, and that will leave me with e to the 3x plus 1, which is perfect, because, and that's my dx. And that's perfect because that's what's in my numerator. So my rewrite would be 1/3 integral of 1 over u du. So that'll be 1/3 ln, absolute value of u plus c. So I'm going to come back to my problem, and on the left-hand side, I end up with y. On the right-hand side, I get 1/3 ln absolute value of e to the 3x plus 3x plus c. Letter A. So for letter B, to separate my variables, I'm going to begin by adding the y over x to the right-hand side. So I get dy dx is equal to yx. I'm going to divide the y to the left side, and I'm going to get the dx over on the right-hand side. And so on the left-hand side, this is the same thing as 1 over y. Sometimes separating that apart just helps to see the integration easier. So when I integrate on the left-hand side, I get ln, absolute value of y, equal to, on the right-hand side, x squared over 2 plus c. Now remember, this is where our algebra comes in. We know that ln has a base of e. So to get that out of log form, we're going to take the base of e raised to this power equal to y. So that'll give me y equal to e raised to the x squared over 2 plus c. Now I'm going to show this step, but you don't have to show it in your work unless it's just really helpful to you. That's the same thing as e to the x squared over 2 times e to the c power by properties of exponents. And e to the c power is just c, so that becomes c e to the x squared over 2. So y is equal to c e to the x squared, x squared over 2. So for letter C, I don't see any separation that needs to occur because all of the x variables are on the left-hand side. So I'm just going to change the y prime into dy dx. Well, actually, I'm going to go ahead and get the dx on the right side. So dy is equal to sine of ln of 5x over x dx. So I'm searching my integration strategies, and certainly that's not what I would call a, quote, normal situation. Looks like to me I haven't, well, not looks like, I can see that I have an inside function right here. Ln of 5x is inside of sine. So I'm going to try letting u equal to ln 5x. The derivative of ln is u prime, which is 5 over u dx. Of course, that is 1 over x dx when we reduce, which works out perfectly because I have a 1 over x. So my new integral by substitution then becomes the antiderivative of sine u du. Everything got replaced at, yep, that was replaceable. The antiderivative of sine is negative cosine of u. Now, whenever you do tricky trig, you stop after you do that and you go, all right, what is the derivative of cosine? The derivative of cosine is negative sine times this negative makes a positive. Got it. So I'm going to bring that back over. So the antiderivative of dy is y, and the antiderivative of the right-hand side is the opposite of cosine. Make my resubstitution of ln of 5x plus c. Letter D. Let me clear this off. So in letter D, let's see, it looks like the only variable I have is x, so I need to get that square root of x minus 2 to the right side. So I'm going to keep the dy on the left. I'm going to multiply and get x squared plus 1. Now it's going to be times the square root of x minus 2, and the dx will be there. Okay. So let's see, what is my strategy going to be for this particular integration? We could distribute the square root into the binomial, but I think that's just going to make the problem messier and messier. It's not an inverse trig because that square root is not in the denominator, so I'm not thinking about that. So the only thing I'm just going to start by looking at the inside function of x minus 2. Yeah, that's how, well, I could let u equal to x squared. Well, let's just go ahead and play that out. Just show the dead ending. So if I let u equal to x squared plus 1, du is equal to 2x dx, and of course I can get the 2 on the other side. Now, when I look back over, I don't just have an x dx, I have a square root of x minus 2 dx. So that really didn't get me anywhere, so I'm not going to, that means I just picked the wrong u. Doesn't mean I'm done, doesn't mean I don't know what I'm doing. So now I'm going to pick the inside function of x minus 2, and du is equal to, excuse me, dx. So that will take care of the x minus 2. I still have a very stubborn, hint, 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 a stubborn x that's not leaving. Now don't be worried because, oh, there's a plus 1. That doesn't matter. Or I think. Let's see. So I'm going to find a replacement for x. So I'm going to add 2 to the other side, and x is equal to u plus 2. So let's see how things go here. In place of x, I'm going to substitute the u plus 2, which is going to get squared. And 1 will be added to that. And then that's going to be multiplied by u to the 1/2 power. So if I square the binomial, I'll get u squared plus 4u plus 4 plus 1 multiplied by u to the 1/2 power. Simplifying that gives me u squared plus 4u plus 5 multiplied u to the 1/2 power. I'm going to distribute the u to the 1/2 power, and that gives me, ooh, that's an ugly integral symbol, u to the 4/2, 5/2 power plus 4u to the 3/2 power plus 5u to, oh, this is working out nicely. I had to do a little algebra to get there, but it's working. Right, now I'm going to integrate, and that'll give me u to the 7/2 multiplied by 2/7 plus u to the 5/2 multiplied by 2/5 would be 8/5. Be careful. Oops, let's don't do the 5 yet because we got to do the power. Come on, erase. There we go. U to the 3/2 times 2/3 would give me 10/3 plus c. Right, so that is the reversing by the power rule. Let's come back over to our original problem. So the antiderivative on the left side is y, and on the right side, make all the replacements. So 2 times u is equal to x minus 2. X minus 2, 7/2 plus 8. U is x minus 2, 5/2 over 5 plus 10. X minus 2, 3/2 over 3 plus c. And that's my last integration for, differential equation. Problem 4, I'm looking for the value of y of pi. I have a differential equation right here that I need to solve, and I have an initial condition that's going to allow me to find the value of c. So I'm going to separate the variables. So I will have dy. I'm going to get the dx on the other side. 8e to the negative 2x minus 2 sine x dx. The left side integration is a glorious y, but on the right hand side I have two terms, term number 1 and term number 2. Term number 2 looks just fine. I know how to find the antiderivative of sine, but term number 1, I have something going on with the power of e. So for term number 1, I'm going to let u equal to the power of negative 2x. du is negative 2 dx. I don't need that negative 2, so I'm going to take it to the other side by division, and that gives me a dx. So my new integral for term number 1 only is negative 1/2. Antiderivative of, let's go ahead and get that 8 out there. I'll make that a 4 in just a second. E to the u du. So that's negative 4. Antiderivative of e to the u is e to the u. Okay, let's see. Let's bring that back over to our problem. So that term number 1 is going to be negative 4 e to the negative 2x power. For term number 2, it's normal, and the antiderivative of negative sine is positive cosine. So I'll get 2 cosine x. Now stop, tricky trig, and take the derivative of cosine. The derivative of cosine is negative sine, so I got my trig correct, and then there is my plus c. Alright, I have my initial condition of 0, 4. So 4 goes in place of y, 0 goes in place of x. So if I substitute 0 in place of x, that will give me e to the 0, which is 1. And 1 times negative 4 is negative 4. If I substitute 0 into cosine, the cosine of 0, the x value at 0 is 1. And 1 times 2 is 2, so that's plus 2 plus c. So 4 is equal to negative 2 plus c. Add 2 to the other side, so c is 6. So our final function is, now we're still not done, we have one more thing to do. Y equal to negative 4 e to the negative 2x plus 2 cosine of x plus 6. All right, now we're going to evaluate that at pi. So y of pi is equal to negative 4e to the negative 2 pi plus 2 cosine of pi plus 6. The cosine of pi, so the x value at pi is negative 1, so that's going to make this a negative 2. And negative 2 plus 6 is 4, so my final is negative 4e negative 2 pi plus 4 is equal to y of pi.